how combining the Internet of Things and machine learning technology can be used to drive and improve haulage efficiency. This is what our business does, but what I'll try to do is discuss these techniques and these ideas in more general terms so that they can be applied whether you're a Cascadia platform subscriber or if you have other questions or other objectives to solve. So in terms of an agenda, what I'm going to do is provide a bit of an introduction to machine learning. I'll talk about how machine learning can and ways to apply machine learning technology to the mining space and specifically to haulage. I'll talk about building an IoT pipeline. In many cases, that might be something that you just hire someone out to do, like an FMS company, but it is a critical part of collecting the information that's needed to inform a machine learning initiative. And then what I'll do is I'll talk about how we've addressed these challenges and how we've solved some of these problems and provide some case studies. And then, of course, I'll be happy to take questions from the audience. So, machine learning is a word that's everywhere. And in many cases, my sense is that people throw the word around and don't necessarily understand if their audience has an appreciation for what we're talking about. So in the context of this presentation, I'm talking about supervised learning, which means we are going to train models by giving the computer examples of inputs and outputs historically. And then what we'll do is we'll ask the computer to run algorithms to build mathematical models based on that training data to make predictions or help us make decisions. So it's the idea of giving a computer information and asking it to identify relationships, make predictions, produce decisions for us or with us. Just very quickly, a few terms that you've likely heard. Linear regression and neural networks, I'm sure, are probably, if you've had any exposure to ML, these are probably the first things you hear about. I will discuss them briefly because they're things that we use, to be honest, on a daily basis in our business. So linear regression is kind of where people will typically start if they're getting into machine learning. The nice thing with the machine learning model is it's very easy to understand. It's very easy to share. You can just send someone a spreadsheet. The mathematics that go into understanding a linear model once it's been built, it's just multiplication and addition. So it couldn't be simpler. And one of the things that's great about them, in addition to their simplicity, is that they're very good at illustrating the relative importance or the relative impact of each of your variables that you go into training your models. But they're not great in some ways. They don't deal well with discrete parameters. And they don't deal well with nonlinearity. And so that nonlinearity piece was the origin or the reason for neural networks. And neural networks is a fancy way of combining lots of linear regression models together to deal with nonlinear relationships. So if the relationship between tonnage and fuel use was not linear, if it was a squared relationship or some other relationship, a neural net could help get beyond the simplicity of a linear regression model. And then the last one I'm going to talk about GBTs because we use them in our business, but really any kind of a decision tree model is when you kind of look at if then else decision-making and analysis. So for example, if a haul cycle was completed on truck A, then we're going to go down this pathway of making a prediction. But if it was completed on truck B, we'll go down a different path and so on and so forth. So, now that we've talked a bit about machine learning in general, what are some good ways or some important and useful ways to leverage machine learning in the mining space? And there's 4 ways that we've identified that we use ML to the benefit of our customers. And I'm going to give an example of each of these at the end of the presentation. But what these are is, number 1, isolating for impact. So understanding how the inputs to our model, and I'll get specific, but how the inputs to our model impact the outcomes we're looking to predict or the outcomes we're looking to better understand. These tools can be very good for evaluating alternatives, so A/B testing. So if you're a mine operator looking to understand, if you should change a speed limit or change a component or purchase a new type of fuel or lubricant, ML tools can be very good for evaluating the different opportunities at your disposal. Of course, predicting future outcomes. So for example, looking at historical activity to predict how things will work as your mine site evolves. Perhaps your pits are getting deeper or your extraction is moving farther away from processing. Your haul cycles might be getting shorter or longer. How is that going to reflect itself in terms of the production you're going to produce and the fuel you're going to consume? And then finally, we can use these models to identify changes that might not otherwise jump out at us by just looking at raw data. So by looking at how how the model can identify a change in your operation, and that can lead you down a path of discovery and process improvement. So let's talk about how you can start to apply ML techniques in your business. And so before you get started, there's three things I'd have you think about. Do you have the right data to answer the question? And so in a supervised learning framework, you want to make sure that you're measuring the inputs that you think are necessary to predict your outcomes. That's not always a simple task, but if you're starting with a good bit of domain knowledge, and in my experience in mining, there's a lot of domain expertise around mines, and people understand the important factors. They just don't necessarily understand exactly how they interact and how they predict or produce outcomes. The next thing is, can you draw accurate conclusions? So can you actually use the inputs you've identified to predict what you're trying to, or answer the question you're trying to solve? And then, of course, do these conclusions lead you to decision making? Can you make a decision? Can you change something? And further to this point is, do you actually possess the levers of control to make a change when you've identified something that could be improved or something that could be made better? And so once you've done those kind of preliminary thought experiments, you can get down to actually going through the motions of using ML to your benefit. So, what does this look like? And on the left-hand side, I've got kind of the steps. On the right, I've got an example that we typically do for large oil and gas companies, which is demonstrating to their customers that a premium fuel or lubricant or catalyst actually produces a benefit to those who use that in their fuel. And so an example of this would be, what impact does a diesel additive have on efficiency, on haulage efficiency? You can then set clear measurement priorities. So exactly what efficiency gain, if any, can be attributed to the additive being included in the operation. Of course, the next step would be collecting data. And so in this example, that would be measuring haulage efficiency, looking at truck and equipment utilization without the additive, building a baseline, and then making that change, applying an additive, and then looking to see how that change unfolds in terms of an efficiency improvement. Analyzing that data, many times that involves kind of digging deeper to make sure that you have the ability to correct or identify other things that might be influencing your analysis. In this example, what we do is we look for significant maintenance activities that might be throwing us off the scent. Or looking at component failures that might otherwise inject change that we want to make sure we manage and account for. And then finally, interpreting results. So those are the kind of 5 general steps. And hopefully that was a bit helpful, giving you a bit of a concrete example of evaluating an additive, but I'll get more specific as we go. So the next thing I said, so in the title of this presentation, I talked about both ML and IoT. And again, that's because that's what we do and that's our business. And so I'll talk about our IoT pipeline, but you might have a different problem you want to solve. You might want to bring back different sensor information, plant information, and what have you. But regardless of what you're trying to connect to your cloud or to your on-prem solution, the steps are likely going to be the same. And those steps I've got listed here are sample. So the actual task of collecting that piece of data, propagation. So propagating that data from where it is in some remote location on some deployed piece of equipment or plant. And so that can take many forms, whether it's cellular or Wi-Fi or whatever. Ingestion, so the process of bringing that data into an organized and curated repository for your data. Historically, that was often SQL servers, lots and lots. Now we're seeing more, different architectures, NoSQL DBs, and these kinds of things are data historians. And then data cleaning. So this is something that I certainly didn't fully appreciate when we started this business, was how critical applying cleaning and cleaning routines to your data is to make sure that you get reliable decision-making and decision intelligence from your data. And the last would be present and interpret, where these last steps are effectively where we train and interrogate our models to make decisions. In terms of our approach, to get a bit more specific, we typically apply these techniques to 2 kinds of models. The first kind of model we build is a whole cycle model. So what we'll do is we'll train a model to understand the specifics of whole cycle activity in order to predict or to understand how those inputs influence production and productivity, as well as haulage efficiency. So the inputs that we are most commonly looking at are tonnage, so how much material is in the dump body, who is operating the piece of equipment, what equipment was in use. Vertical travel is something that we've identified as a critical component to understanding haulage efficiency. So vertical travel in the loaded state is probably the single best or the single strongest influencer of haulage efficiency and consumption. What distance was traveled, how long did the cycle take? Does that include extra time spent idling, queuing, spotting, these kinds of things? Geolocation, where in the mine was this data captured? And that really gets to the heart of things like road condition, underfoot condition, these kinds of things. And then even seasonality, because if you're looking at a mine over time, you have to account for the fact that specifically in places like where I live in Canada, there is quite a dramatic difference between operation in the summer months and in the winter months. And then, of course, the outputs that we look for in our haulage modeling relate to liters per cycle. How much fuel will a cycle that has been characterized in the following terms consume? We also look at production in terms of things like tons per hour, and then efficiency in terms of things like liters per ton or per ton km. The other type of modeling that we look at is road segment analysis. So identifying a segment of road to understand how tonnage, vertical travel, distance and time and seasonality are going to influence the speed we're going to carry across that segment, how long it's going to take to cover that segment, how much fuel we're going to burn in those contexts. And so these are the models we use. And what we're going to talk about as we go forward is how we use those models to answer questions that, that people like this audience would care about. In terms of our approach to data sampling, so typically we sample data every tip event, every dump body load event, and every unload event. We also collect data on a time series basis and in response to exceptions or exceedances or alarms. Okay, so those will be the things that we use to kick off or initiate a data capture. And in terms of the data we collect, that includes, of course, high precision fuel measurements. So that's what our business is really centered around, is high accuracy, high frequency on equipment fuel measurement. But again, I've also mentioned the importance of vertical travel. So we look at pressure-based altimetry, vehicle network connectivity. So that's CAN bus, CAT data link, Komatsu PLM, depending on the flavor of the equipment. 9-axis motion sensing, which gives us access to vibration, acceleration and deceleration events, as well as ramp grade. Geolocation, so where are we in the mine, what ramp, what pit are we working on? And then we're also expanding our data set to look at things like oil condition sensing, tire pressure monitoring, and just expansive capacity to bring on new sensors that might have relevance as we look at new use cases and new opportunities. So again, in terms of our approach, our sampling hardware is what you're seeing here. So that upper image, that upper circle is an example of our remote GPS device. Our IoT device is the middle circle, and an example of a high precision volume meter, fuel meter, is that aluminum block you see at the bottom. And again, we do some continuous measurements as well as time triggered samples in order to inform our sample. The next steps in that data pipeline are propagation. So again, depending on how your mine is connected, that might be cellular, that might be 4G or eventually 5G as those networks come online. Wi-Fi is still very common. And in some cases, what we find is mines will have Ethernet, a switch per device, and then you're integrating on the device level. The key, though, is making sure you've got a reliable data pipe from your IoT equipment to your ingestion point. And then, of course, ingestion is the process of bringing that data in, unpacking it to the right places, making it understandable and readable, if not by humans, at least by your systems that will train and build models. I mentioned cleaning as an important step in that data propagation pipeline. And so we use microservices. So every ingestion activity kicks off a set of microservices that look at that data, look for erroneous problems, look for things that can be cleaned or recovered or otherwise excluded. And then finally present and analyze. And so again, in our framework, we have a number of visualizations and tools that we show our customers, ways to understand, to on the fly train and interrogate models, even if you're not a data scientist or a machine learning expert. But again, that's kind of the steps. So identify the machine learning question you want answered, the prediction you want to make, the understanding you want to gain, build that data pipe, that IoT pipeline, and then get on with the process of presenting and analyzing the data. So again, I've talked about 4 key ways that mining companies can use machine learning to their benefit. Again, those are predicting future outcomes, evaluating alternatives, isolating for impact, and detecting changes. And this first example I'm going to talk about from a US gold operation. In fact, it was the operation I was at a few hours ago, and I'm actually presenting from a hotel room. This mine was actually looking to change their road. So if you look at the lower central image, what you're seeing is an example of how the mine operated until about June of this year. And you can see that kind of dogleg rounded path that the trucks were forced to take. And the mine wanted to understand what would the impact be on both production and efficiency if they could build a new road to cut that corner. And so we started by doing road segment modeling and analysis to look at the vertical travel that would be required, the distance, the average speeds we could expect. So that upper image on the right side is looking at the relationship between grade and speed. And what we were able to do is use these models to effectively predict the future, predict how the operation would evolve if they cut that corner and straightened out that road. And what we found, based on effectively an hourly operating cost for their haul trucks, these were 789 and 793 cat haul trucks, that the result of this modification would be a $273,000 savings in operating costs. And then, of course, if they could turn those saved hours, worked out to about 20 seconds per haul, that was to the leach pad in this case. If they could turn that saved time into extra production, it could be as much as 425 additional ounces of gold per year, with a price currently sitting around $750,000. And so that was an example of using these tools to predict the future, to inform decision making, to get more out of the mine site. Another good example I talked about is evaluating alternatives. So Alcoa in Australia was pitched on a fuel additive by a company called ADDITIVE. And they asked us to design an experiment that could isolate for the specific impact of applying this additive to their trucks. And so that experiment was run by having, I think in this case, it was 8 trucks. All trucks ran on their baseline fuel. We built a model to understand the efficiency of each of those 8 assets. 4 of those trucks were reconfigured to have the new configuration, the additive pack. And then we looked to see how the 4 control trucks and the 4 test trucks evolved in a second phase of the test, where we could then isolate for the impact of, or compare the alternative of the additivized fuel versus the non-additivized fuel. What you can see in the center bottom, those error bars and red dots effectively show what the models told us was the impact of these additives. And so you can see that those dots all pretty much fell around 3 3/4 to around 5 3/4. But the most reliable model we had, so the model with the tightest error bars, came in around, let's say, 4.25%. And to be honest, this is the highest number that we've ever seen. We've done a lot of this work. This is the highest number we've ever seen, with a statistically significant results. But the thing to take away from this is that those error bars are plus or minus about 0.5, 0.6%. And so for many people, the ability to measure efficiency or to isolate for the impact of some alternative you're considering to within 0.5% is something that hasn't been possible without these techniques, without machine learning, and specifically in this case, without high accuracy fuel measurement devices. The third case study I'll talk about is truck of choice. Most of the mines we work with will look at comparing trucks, at least comparing truck and haulage efficiency in terms of simple metrics like liters per ton kilometer. They might be using an effective flat haul metric, or just liters per hour. And what we find is that if you are evaluating a truck in terms of those metrics without normalizing for utilization, for operator, for seasonality, there's a lot you're going to be missing, or you might be led down the wrong path. And so with machine learning, that third use case, which is isolating for impact, is let's look at the specific impact of the haul truck itself, the metal itself, as opposed to how it was used or who was operating it, and then understand pound for pound which truck is most efficient. And once you have that information, you've got a good starting point if you're looking to answer a question such as, in an over-trucked environment, which truck should I be parking or selling? In a maintenance constrained environment, you might be looking to answer questions about which truck is a priority for repowering or for remanufacture of the engine. Or for example, if you're looking to evaluate competing opportunities for new trucks, what is the best truck that you want to be looking to purchase? And so these are all questions that we help inform by getting down to a modeled, normalized understanding of haulage efficiency once you've corrected for all of the features and factors in mine hauling. The last example is change detection. And so again, if you're just looking at a metric like liters per hour or liters per cycle, you might miss out on an underlying change of a truck or an operation because it might be buried in the noise around variable truck dispatch or other things that make these kinds of assessments very difficult for people to perform without a machine learning or modeled approach. And so if you look at that bottom image, what we're looking at there is some step changes, some very large step changes that we see that might not have been interpreted or recognized by the operation, and then we alert on those and refer those to maintenance or operations to have a look at those types of situations. So I think I'm probably coming up toward the end of my 20-minute slot. But what I'd like to do is certainly take some questions. In summary, what we've done with our business is look at how we can use the data we collect from an IoT pipeline and how machine learning techniques can be used to answer questions that may otherwise historically have been unavailable or too challenging to get to the heart of. In fact, we found a lot of customers had kind of given up on getting data that was good enough to drive some of these decision-making processes. And I think that with the growth of ML and IoT, there's a lot that's going to be possible. And whether your focus is haulage efficiency like it is for us, or whether you're looking at plants improvements or availability gains on the maintenance side, I think there's a lot to be gained by these techniques. So with that, I'd love to take some questions, either about our specific platform or certainly about machine learning and IoT techniques and strategies in general.